We know that the gravitational field, which I am denoting over here with E vector, is nothing but the force per unit mass. So this field is exerted by all objects that have mass. This field points towards the source mass. So this is the mass that is experiencing this particular force. That particular mass is kept in the denominator. So this mass is also called as the test mass. So let us say this is the source mass. This is the source of the gravitational field. This is the source mass. And let us say this is the test mass. So the gravitational field, because of the source, is going to point towards the source, and the gravitational field is going to be given as G, mass of source, into the test mass, which is being represented by the letter small m, upon r square. And this field points towards the source mass. So this is the direction in which it points. So essentially, so this is the force, so we have to divide by the test mass to get the field. So essentially the field is going to be equal to, the magnitude of the field is going to be equal to G, mass of source, upon r square. And as far as the direction is concerned, it's towards the source. So usually the r vector is taken to be pointing from the source to the test mass. So this is the usual r vector. So r cap is going to be a vector that has unit magnitude and is in the direction of r vector. So this we can write is minus r cap. So the gravitational field as a vector quantity will be given as Gm upon r square and minus r cap being the direction. So this is the gravitational field. Now let us understand what would be the gravitational field. Also, the gravitational field is dimensionally the same as acceleration due to gravity caused because of the source mass. So basically, acceleration due to gravity, we can say G, the acceleration due to gravity, is going to be equal to force divided by m as well. So acceleration due to gravity caused by the source mass is going to come out to be the gravitational field only. Let us analyze the case of a hollow sphere. In case of a hollow sphere, there is one interesting phenomena that happens for points that are inside the hollow sphere. We choose diagonally opposite areas so these areas are conically diagonally opposite. So for this particular point, it can be shown that the gravitational field cancels out for these two areas. So this particular area is going to have a gravitational field pointing in this direction. This particular area is going to have a gravitational field pointing in this direction. So they are opposite in direction and they happen to be equal in magnitude. I'll give a hint as to how it is to be proven. So the field is going to be dm upon r square, where r is this particular distance. Okay, so I am labeling this particular distance as r2. Let us say this distance happens to be r2 and this particular distance happens to be r1. So this field is dm2 upon r2 square, of course, into g, and the field, because of area 1, so let us say this is area 1 and this is area 2. So the field because of area 1 happens to be g dm1 upon r1 square. Now what happens is, here dm2 is effectively proportional to r2 square. So you can say that dm2 is going to be some constant sigma into r2 square. So this happens because of the conically vertically opposite angles. So you can say like the conically opposite angles being congruent in steradian major. So these are 3D angles basically. 3D angles are given by d omega is equal to d area upon r square. So these two angles are congruent. So because of that, area upon r square happens to be congruent basically. And if you actually multiply this quantity with the surface mass density, this quantity into surface mass density, which is constant, surface mass density. Now this is going to yield dm basically. So the area into surface mass density, this particular quantity is dm. The r square in the denominator remains as it is, like so. So because of this, what happens is the vertically opposite angles are congruent. So d omega 1 is equal to d omega 2. So that means dA1 upon R1 square is equal to dA2 upon R2 square. So if we do multiply this with the surface mass density, I am calling the surface mass density as K as of now, let us say. If we multiply this with K, then I get dm1 upon R1 square is equal to dm2 upon R2 square. So this is what implies these two things. This is what implies that acceleration to gravity gets cancelled and the gravitational field gets cancelled. If we just multiply this by g, then you are going to get this exact expression to be the same. So these two are equal and opposite, so they cancel each other out. So similarly, essentially what happens is the entire sphere's vertically opposite areas effectively cancel each other's gravitational field for points inside the sphere. So for points inside the sphere, there is no net gravitational field. The net gravity for points inside the sphere happens to be 0. So this particular concept is called as shell theorem. Alright. So let us say we were to find out the fields at points on the surface and beyond the surface. So let us say we are talking about a point that is on the surface or a point that is outside the surface. So the accelerator to gravity for such a point is going to be given as g m upon r square. So this is the magnitude. The direction was obviously directed towards the source mass, so it's directed towards the center. So g is going to be directed towards the center on all these points. So this is for r that is greater than equal to capital R. And E inside we know this is equal to 0. So this is for r less than r. So if we do happen to draw a graph, then we would get, this is the y-axis, this is the x-axis. So we would get in the interior portion, the gravitational field happens to be 0. So that means till you reach the radius r, the gravitational field is going to be 0. So this is the gravitational field till you reach the point r. So we are plotting the gravitational field as a function of r basically. So after you reach the point r, then in that case the gravitational field decreases as 1 upon r square. So it goes like this after the point r. So there is a discontinuity at the point r as far as the gravitational field is concerned. So this you can say is the graph of the gravitational field for a hollow sphere. Now let us analyze what happens in case of a solid sphere. In case of a solid sphere, we can understand that only, so let us say we are analyzing at a point outside. So E at a point outside or on the surface is going to be the very same exact expression, Gm upon R square. So this is for R greater than equal to R. So that expression does not change. So at a point inside, at a point that is inside, only the interior sphere is going to actually contribute. So this is at a distance R from the center. So essentially what is happening is, because of shell theorem that we just learned, this annular region has zero contribution, because this annular region can be divided into small spherical shells, each of infinitesimally small thickness, and because of that it's not going to contribute towards acceleration due to gravity at this particular distance r from the center of the sphere, wherein r is less than the radius of the sphere. So this is a uniform solid sphere. So only the portion that is inside is going to cause acceleration due to gravity. So acceleration to gravity E will be given by the usual formula as G into mass of the inner sphere. So the mass of the sphere is min upon r square. Now mass is proportional to density into volume. So mass is exactly equal to density to volume. It's proportional to volume when density is constant, and we are assuming the density to be constant over here. So mass is going to be equal to 4/3 pi r cube into rho. So this r is the small r, not the capital R. So let me replace it. Yeah, so this r happens to be the small r. So this is min, and the mass of the entire sphere is nothing but m is equal to 4/3 pi capital R cube into rho. So this is the mass of the entire sphere. So when we take the ratio, we understand that because of this, we are going to get min is equal to r cube upon r cube into m. This is what we are going to get. So if we do substitute this in the aforementioned equation, if we put this over here, then we are going to get, so this is E inside. Okay, so we are going to get E inside to be equal to G r cube m upon capital R cube whole divided by r square. So this can be rewritten in a convenient format. So this is Gm upon r square into r upon r. So this is easy to remember as well. Gm upon r square is nothing but the acceleration to gravity at the surface of the sphere. So I am just writing down Gm upon r square as E naught into r upon r. So if we do want to draw the graph of this particular expression, then this happens to be the y-axis, this is the x-axis, then we get that this linearly increases till the distance r, and after the distance r it goes down as 1 upon r square. So this is a continuous graph. So this particular distance is the distance r. So this is, we are drawing E of a uniform solid sphere as a function of r. Now let us take a ring. Now in the particular case of a ring, we want to find out the gravitational field on the axis of the ring. So let's say this is a point on the axis of the ring. We would like to find out the gravitational field at this particular point. Let's say this is the point P on the axis of the ring. Now let's say that the distance of the point P from the center of the ring happens to be equal to small r. Let us say this distance happens to be small r. I'll write down that distance. this distance is small r. Now the radius of the ring is assumed to be capital R. Let us say radius of the ring is capital R. Now it is easy to understand that because of this particular small mass dm, the ring's gravitational field is going to be pointing from the point P towards this mass dm essentially. This is the direction in which the gravitational field is going to be pointing, this particular direction. Alright, and what is going to be the magnitude of this field because of the small mass? It's going to be dE is equal to G dm upon R. So this happens to be, let us say, instead of R square, I'll use the notation L. Let us say L is the length over here, or rather instead of L, I would choose to use the notation, let's say P. This is the distance P. So G dm upon P square happens to be the magnitude of the gravitational field. Now this particular gravitational field is pointing as shown from the point P towards the small mass dm. So this is the small mass dm. However, this particular field has two components. One is the vertically upward component and one is the horizontal component towards the left. Now this vertically upward component gets cancelled because of the opposite point's gravitational field having a vertically downward component. So the only component that essentially survives is the leftward component. And once we understand this particular concept or this particular realization strikes us, we can understand that the only field to be surviving is going to be dEx, the field in the x direction. This x, so this direction is defined as the x direction. So dEx is going to survive, the horizontal field is going to survive, and the vertical field is going to get cancelled out. So dEx happens to be G, so let this angle be theta. So it happens to be G dm upon P square cos theta. Alright, so we now can easily understand the fact that cos theta happens to be equal to R upon P, and P happens to be equal to under root of R square plus capital R square plus small r square because of Pythagoras theorem. So basically dE in the x direction, which is the only surviving gravitational field, is going to be equal to G dm. Instead of cos theta, we'll write down as R divided by P, and there is a P square over here. So this comes out to be G dm R divided by P cube. So this is going to be equal to G dm R upon x square plus, not x square, small r square plus capital R square raised to 3 by 2, because small r square plus capital R square raised to half happens to be P. Now we are cubing P, so basically it's going to be small r square plus capital R square raised to 3 by 2 in the denominator. So this is dE in the x direction. Okay, so if we do integrate this, we need to now understand that the only variable is the mass dm. Everything else is a constant over here. So integrating dE, we get, so if I just integrate this particular expression, we get everything else to be constant, hence it will come out of the integral sign. So this is equal to G R upon R square plus capital R square raised to 3 by 2 into integration of dm. Integration of dm is nothing but the total mass of the source ring. So it is going to be g m r, m is the total mass of the ring, upon r square plus r square raised to 3 by 2. So this is the expression for E, which all Ex, which also happens to be the net field. So let me box this particular expression. This is the exact expression. It would be useful if the student remembers this expression for solving problems related to gravitation. Now let us go ahead and understand the field of a disk. So this particular disk, in order to, if we want to integrate and calculate the field of this particular disk, then we actually would have to divide this disk into small thin infinitesimally small rings. Now the total mass of this disk is m. So mass of any one such ring is going to be given as 2 pi r dr, which happens to be the small area of that ring, into sigma. Sigma happens to be mass per unit area. So this is nothing but dm. So this comes out to be 2 pi r dr into mass upon pi capital R square, where capital R is the radius of the entire ring. So this radius is capital R essentially. So if we cancel out pi from this expression, we get 2r dr into m upon r square to be the mass dm. So at a point, let us say P, that is at a distance of small r from the center. So this distance happens to be small r, let us say. So at this particular point P, the gravitational field would be pointing towards, for this particular ring or this particular small mass dm, the gravitational field will be pointing towards this point, and only the horizontal component will survive. So we already know the expression for the gravitational field of such a small, infinitesimally small thickness ring. So basically what we are doing is we are dividing the disk into infinitely many infinitesimally small rings, each of variable radius r and thickness dr. So the area of that ring dA is nothing but 2 pi r dr. Okay, so essentially what is going to happen is, if when we set up the integral, we are going to get Ex as being equal to g dm Okay, so here there are two r's, so I need to change the notation. So I will use x as the notation for the radius of the ring. So this notation has to be x, because r is the distance from the center to the point P. So this notation we can change to be x. This is the notation x basically. Alright. So we can write down this to be g dm upon, okay, so g dm into r upon x square plus r square raised to 3 by 2. So from here, when we plug in the value of dm from over here, then we are going to get this to be equal to g 2x dx m r upon x square plus r square raised to 3 by 2. So this is the small field E because of the one small ring of radius x and thickness dx. So the dA of that ring is 2 pi x dx. I need to change the dA as well. Here we can carry out this particular integration by using the substitution. There is a substitution we can use here. X square plus r square is equal to x square plus r square is equal to, let us say p square. Let us say if we put this, then we can write down 2x dx as being equal to 2p dp. So this entire expression changes to integration of g 2p dp into mr upon p square raised to 3 by 2. So because of this, we can understand that it's p cube in the numerator, p in the numerator, so 1 upon p square is going to come. So g into 2mr dp upon p square. This is the integral that remains. So this is g 2mr p raised to minus 2 has an integration of p raised to minus 1 upon minus 1. So the integration of this is p raised to minus 1 upon minus 1, where p happens to be equal to under root of x square plus r square. Alright, so after we put the limits, what are the limits? From 0 to capital R being the radius of the disk. So after we put the limits, we get the final expression of the field to be E is equal to 2gm r upon capital R square into bracket 1 upon r minus 1 upon root of r square plus r square. So this is the exact expression. So this particular expression we can say is the exact expression. This expression can also be written down in terms of the angle theta from the point P to the edge of the disk. So basically this particular angle, let us say this angle is theta, this angle till the edge of the disk, then this particular expression can also be written down as E is equal to 2gm upon r square into bracket 1 minus cos theta. So it can be rewritten as this as well. This also happens to be an exact expression that is relatively easier to remember, because cos theta happens to be equal to r upon under root of x r square plus small r square. So cos theta here happens to be r upon under root of r square plus r square. Alright. Now let us take the case of a rod that is, as of now, let's assume the rod to be finite in length, and later we'll relax that condition and make the rod infinitely long in length. So let us say we have a point P at a perpendicular distance r from the rod. So let us say this is the perpendicular distance r from the rod, and this is the point P that we are talking about. So we would like to find out the gravitational field at such a point P. Now, in order to do that, we need to define the linear mass density of the ring lambda. So let us say lambda is going to be equal to mass per unit length. This is specified and given. So if I choose my origin of coordinate axis to be over here and x-axis in this particular direction, so this is my x-axis, and y-axis in the direction that is parallel to the rod, then in such a case I'll get, or I can write this as dy, and the mass that this dy holds, dm, is nothing but lambda times dy. Now let us say this angle happens to be the angle theta. So this is the angle theta. dE for this particular mass is going to be g dm. Obviously it will be pointing towards the mass, so but it's going to be g dm upon, so this particular distance, so this is y, so this particular distance is under root of y square plus r square. So this is going to be g dm upon under root of y square plus r square, the whole square. So this is going to be equal to g dm upon y square plus r square. Alright, so as of now we are interested in the horizontal component. It's not that for a finite rod only the horizontal component will survive, but we are going to go to an infinite rod. We would like to derive the expression for the infinite rod, so we are essentially interested in the horizontal component. The horizontal component will be given as g dm upon y square plus r square into cos theta. Now cos theta happens to be r upon under root of y square plus r square, and dm happens to be lambda times dy. So we can write down this expression as g lambda dy. Cos theta is nothing but r upon under root of y square plus r square. So here I get this dE in the x direction to be g lambda r dy upon y square plus r square raised to 3 by 2. Now on integrating this particular expression, we get the total horizontal gravitational field because of an infinite rod. So here the only variable is y in this particular expression. We can choose to write down y in terms of theta. We know that y upon r is equal to tan theta. Therefore y is equal to r tan theta, and dy is equal to r sec square theta d theta. So if we do make these substitutions, we can understand that this expression is going to become g lambda r, dy will be r sec square theta d theta, and in the denominator we'll get y square plus r square. Y is r tan theta, so that will be r square 1 plus tan square theta raised to 3 by 2. So that is sec square theta raised to 3 by 2. That is sec cube theta in the denominator. So sec square theta upon sec cube theta is going to give you 1 upon sec theta. So in the numerator you will get cos theta, and RR is going to get cancelled, leaving only one r in the denominator because there is effectively r cube in the denominator. So this whole thing is raised to 3 by 2. So you are essentially, after mathematics, you are going to get g lambda upon r cos theta d theta. That makes it much easier to integrate. So let us say this rod is going from minus theta, or let us say the endpoints of this rod, and label the endpoints with blue. Let us say the endpoints of this rod are minus theta to plus theta. Let us say this particular angle happens to be theta 2 and this particular angle happens to be theta 1. Then in such a case, the limit of integration will be from minus theta 2 to theta 1, because we are moving from below the x-axis to above the x-axis as we move from theta 2 to theta 1. So we'll have to take the limit as minus theta 2. So integration of cos theta happens to be sin theta. So Ex is going to be equal to g lambda upon r. This happens to be sin theta, g lambda upon r sin theta from minus theta 2 to theta 1. So it's sin theta 1. This can be written as g lambda upon r sin of theta 1 minus sin of minus theta 2. So minus minus will become positive. So I'll essentially get Ex is equal to g lambda upon r sin of theta 1 plus sin of theta 2. So this is the exact expression for a finite rod. This is the acceleration to gravity in the x direction for a finite rod. Similarly, we can find out in the y direction by taking the component sin theta instead of cos theta and integrating. That exercise I leave for the student to pursue. Also, now if we move on to an infinite rod, so this is for a finite rod. Finite rod. Finite uniform rod. So if we move on to an infinite rod, then in that case we would simply have to put the angle theta 1 and theta 2, both of them, to be 90 degree. So let us say we do that, then we get Ex for an infinite rod to be equal to, so sin 90 plus sin 90 is going to be 1 plus 1, which is 2. So it is going to come out to be g lambda into 2 upon r. So this is the expression for an infinite rod. Alright. So recapitulating, we derived the expression for acceleration due to gravity for a hollow sphere along with the graph inside and outside. So here we saw that because of Shell theorem, the gravitational field inside the hollow sphere happens to be 0. Then we went ahead and derived the same for a solid sphere. So inside the solid sphere, the field happens to be E naught into r by r. So this being the exact expression for the solid sphere, En is gm upon r square into r by r, and E out is going to be gm upon r square. So next we went on to do the same for a ring along the axis of along the symmetric axis of the ring basically. So the expression that we got over here is gmr upon r square plus r square raised to 3 by 2, where small r is the distance of the point P at which the field due to the ring was to be found out from the center of the ring, and capital R is the radius of the ring. We went on and did the integration for a disk. For a disk, we got the expression E is equal to 2gm small r upon capital R square into bracket 1 upon r minus 1 upon root of r square plus r square, which could be simply written down as E is equal to 2gm upon capital R square 1 minus cos theta. Theta being the angle between the edge of the disk and the line joining the center of the disk to the point P. Then we went on to derive the expression for a finite rod, derive the expression of the gravitational field in the perpendicular direction for a finite rod. So this is the direction perpendicular to the rod, and there will be a field parallel also for a finite rod, but that expression I have left for the student to derive on their own. So for the parallel expression, you'll have to write dEy, and here you'll have to take sine theta instead of cos theta. The rest of the integral you can pursue in similar manner. So basically, for a finite rod, the expression is g lambda upon r sine theta 1 plus sine theta 2. This is uniform finite rod, and if we do extend this rod to plus and minus infinity, then this thetas become 90 degrees. So the theta 1 becomes plus 90 and theta 2 becomes minus 90 degree. So in such a case, basically, you'll get sine 90 plus sine 90. So here you'll get 2 essentially. So the magnitude of theta 2 is 90 degrees, so we'll have to substitute the magnitude of theta 2 over here, because along with the sign we already substituted by taking integration. So Ex will be g lambda upon r sine theta 1 plus sine theta 2, which is g lambda into 2 upon r. So that is the expression. 2g lambda upon r is the expression for an infinite rod. So this is an infinite uniform rod. So the student is advised to remember all these expressions by heart.